Started recording. Okay, so welcome back. We are meeting after a few days, right? Wednesdays and Fridays. So Friday to Wednesday, many days in between. I see 13 students are there already. Okay, so let's start by recalling what we did last time, and then we will go through the slides for today's class. As usual, we will take a small break, and you got my message yesterday that the remaining problems you go through it. So we will have a shorter break today, maybe, since you had a chance to go through the problems already, right? Okay, so let's go to the slides. So let me share the screen. Yeah, you can see the screen, no? You can see the Beamer file, right? Can someone just confirm? Yes, yeah. Because last time I forgot, so this time it's okay. So third lecture today. So the main points that we are going to cover today are these things. Again, I think all these things you know from your last course, but we will follow Rodin's approach and quickly go through these things. So we will have winding number, local Cauchy theorem. I am putting this word local because we will have a much more general Cauchy theorem, what is called the global Cauchy theorem, a bit later. And then we will have Cauchy integral formula, not the most general form that will follow in global Cauchy's theorem, but we will have it in a convex set today, and we will have Morera's theorem. Okay. So what did we do last time? Last lecture we discussed the power series, and we basically did two things, right? So it will come in the slides, but let me try to recall. Uh, so basically 2 points we had about power series. One is that if you have a power series, then it is differentiable everywhere. It's holomorphic. And the basic idea is term by term differentiation can be rigorously justified. So that we did. And the other thing we had was, yeah, now that a function is representable by power series, we define when do we say a function is representable by power series, and then we wanted to construct. I hope it's okay. It started to rain here. But if there's too much disturbance at that time, you let me know. If you can hear me clearly, let's continue. So yeah, functions representable by a power series. Then if a function is representable by a power series, then of course it's holomorphic because power series can be differentiated term by term. And then the question was, how do we construct such functions? And then there was this basic method by what I call suitably integrating, right? And we take a curve and take a path and integrate 1 by zeta minus z with respect to zeta, integral d zeta by zeta minus z, and we showed that this is representable by power series. What was the basic idea, if you recall? The point is by our choices, so you take a disk and then you have to get a power series expansion there, and we were doing a manipulation and comparing it with the geometric series. This was the basic idea. So geometric series would give you this quantity 1 by zeta minus z. It will have an infinite expansion. It will have a geometric series expansion. I hope you recall this. And then we wanted to take integral of d zeta by zeta minus z. And you had an expansion, and you take term by term integration. And this term by term integration, integral of the sum is sum of the integral, needed a justification, and this basically followed by uniform convergence of the geometric series, basically. So this was the idea. So this is what are there in the slides. So we discussed functions representable by power series also, and we saw that such functions are holomorphic, and moreover the derivative of such a function is also representable by power series, can differentiate term by term. That was the point. And then we discussed an important, I have a message here. Okay. So then we discussed the important result, which is what I just recalled, how to manufacture a lot of functions representable by power series. This was easy. It was a geometric series idea, and we did that also. By suitably integrating, we can manufacture functions representable by power series. So quickly recall this, we have already done that. And today we will discuss the winding number. You must have seen this already. We will go through that once again. And also the local Cauchy theorem. So we will prove the Cauchy theorem in a convex set, in a convex open set. As corollaries, we will prove the Cauchy integral formula in a convex set, and we will also prove Morera's theorem. So this is what is there in the menu today. Okay. And of course, after some time, we will take a break and we will discuss. So whatever I put usually in a gray box, maybe there are certain things in a gray box on my slides. That of course we will discuss in the break. And last time we had 5 problems. I think 2 we did. Other 3 I asked you to do. Maybe quickly we can discuss that also. Okay, so that's the plan. So let's come to winding number. Let's come to winding number. So start with a closed path. Okay, we are talking about winding. So you have a closed path and consider its complement, the points outside the closed path. The range of the path is what is denoted by gamma star. So consider the complement and define. So this is what I call the winding number. So what is the definition? It is the integral that we considered earlier, d zeta by zeta minus z. Now the path is closed. Okay. Earlier when we analyzed representable by power series etc., I took any path. Now the path is closed. It's the same integral normalized by dividing by 2 pi I. So this is defined for any z in omega, and we are going to prove that this is an integer valued function. This number, this complex number is going to be an integer. It could be positive, negative, 0, but an integer. And depending on how omega is, how gamma is, omega may have many components, right? Connected components. Omega may have many connected components, and we are going to prove that this is an integer. And if you take a point from in omega, and if you take any other point in its connected component, so if you take 2 points from the same connected component, we are going to say that it's a constant. So if at one point, if it is some number, let's say 3, then if you take any other point from the same component, for that point also it's going to be 3, right? So induced Z1 are not induced. Index of this is called index of Z1 and index of Z2 will be the same if Z1 and Z2 are from the same component. This we are going to prove, and then we are going to prove that this integer is 0 in the unbounded component. Notice that I have underlined the, because there will be exactly one unbounded component, and there the value will be 0. If z is from the unbounded component, the value will be 0. Okay, statement is clear? Yeah, so let's see how to prove this. And this is called the index. For index of z with respect to gamma. Index of z with respect to gamma, or some people call it the winding number of gamma around z. How many times gamma is winding around z? So index of z with respect to gamma, or the winding number of gamma around z. Okay, so what do we need to do? Yeah.
Sir, so I have a doubt. So, is this going to wind clockwise or anti-clockwise?
Doesn't matter because depending on the orientation of gamma, you can take gamma clockwise if you want, you can take gamma anti-clockwise if you want. It's up to you.
Okay.
Whatever orientation of gamma you take, you will get an integer. That's all that we are saying. So if you change the, suppose you give me an orientation, I get 5, and if I take the opposite orientation, I'll get -5.
Okay,
Clear?
sir. Got it.
Yeah. So we are only claiming it's an integer. Okay, no, nothing about the orientation right now. Okay, so let's prove this. So here is an easy proof. So we are going to show that this is an integer, and then we have to show that it's constant on components and also 0 in the unbounded components. So first let's show it's an integer. Now what is the idea? So before I come to the slides, maybe I'll just verbally say something and then let's go through the slides quickly. Okay. So tell me on WhatsApp later if this method is good or going through the slides slowly from starting is a good idea. Okay. So so gamma is a path, you can parameterize it. So there will be a parameterizing interval AB. Gamma is closed, so gamma of A equal to gamma of B. The starting point and the end point are the same. We want to show that something is an integer, right? And what will be our idea? How does one show something is an integer? One way of course is, see, suppose you have a complex number W, and W is an integer, same as saying e power, the exponential of 2 pi I W is 1. So in other words, W by 2 pi I is an integer if and only if e power W is 1. So we have to show that this is an integer. So call this W. This integral if you call W, W by 2 pi I is an integer if you have to show. It's enough to show that e power this part is 1. Okay, what is this part? Integral gamma this? This will be integral a to b gamma prime s ds by gamma s minus z, right? Using the parameterization. So you have to show that e power that integral a to b e power integral a to b gamma prime s ds by gamma s minus z is 1. This is what we have to show. So with this in mind, we consider this function phi of t, which is exponential of integral a to t. We have to show integral a to b of this is 1. So I am considering a function with variable t, a to t, exponential integral a to t of this. Okay, so this will be a function defined on the interval a to b. And what is our aim now? In order to show that this is an integer, we have to show that e power this is 1, which is phi of b, exponential of integral a to b, this is 1. That's what we have to show. So we have to show that phi of b equal to 1. We have defined this function phi t, analyze this function a little bit and conclude that phi of b equal to 1. That's what we have to show. So the idea is to show that phi, yeah, we have to show that phi of b is 1. So let's see. So aim of showing phi of b is 1. Okay, all of you are here with me till now. Now what we are going to do is, yeah, somebody has a question? Okay, yeah, go ahead. Who has the question? Surya Pratap Singh has a question? No, Chirag, yeah. Chirag,
So
ask.
no, sir. Like, I did by mistake. No, I don't have any question.
Okay, fine, good. So let's go back. So this is what we have to show. Now, what is gamma? It's a path. Path means what? Piecewise continuously differentiable. So you can subdivide this into finitely many intervals, and in each interval, it's continuously differentiable. And you can check in particular, it's a continuous function throughout, right? follows from the definition of piecewise continuously differentiable that it's also continuous. So suppose gamma is differentiable. Okay, if gamma is differentiable, then gamma prime, suppose it's continuously differentiable throughout, then gamma prime is continuous. So this is a continuous function, and the integral of that will be a differentiable function. Exponential of a differentiable function will be differentiable, and phi will be differentiable, right? And what will be phi prime of t? It will be exponential of this times the derivative of this, and derivative of this will be the integrand by the fundamental theorem. So you can compute phi prime of t. Phi prime of t will be phi of t, because it's an exponential, it will not change, times the derivative of this, which will be gamma prime t by gamma t minus z. This is the case if gamma is differentiable everywhere. Right, you will get phi prime t equal to phi t times this. So I have taken phi t downstairs. So phi prime t by phi t equal to gamma prime t by gamma t minus z. You will get this wherever gamma is differentiable. Phi t is okay, no, I can take phi t down, right? Why? Because it's an exponential function, it's never zero. So phi t is never zero, so this is okay. And I will get this equation whenever gamma is differentiable, wherever gamma is differentiable, and where is gamma differentiable? Gamma is differentiable everywhere except possibly at finitely many points. So all those places you are going to get this formula, going to get this identity, right? Now if you cross multiply and see what is happening, so this means gamma t minus z times phi prime t minus phi t times gamma prime t by a denominator is equal to 0, right? Just cross multiply and take one to the other side. So gamma t minus z times phi prime t minus phi t times gamma prime t divided by something equal to 0. In particular, the numerator is 0. So what that means is, you can consider this function phi t by gamma t minus z. And what will be the derivative of this? Derivative of this is gamma t minus z times phi prime t minus phi t times gamma prime t. So that's exactly the numerator here when you take it to one side and cross multiply and take it to one side. So that is 0. That is 0 at all those points where gamma is differentiable. From this you can conclude that this function, whose derivative is 0 wherever gamma is differentiable, from that you can conclude that wherever gamma is differentiable, this function is a constant because its derivative is 0. But then you can conclude that it's a constant everywhere. Why? Because there are finitely many subintervals, everywhere it's a constant, and throughout this is a continuous function. Gamma is continuous because it's piecewise differentiable. The continuity of phi also follows from that. So this is continuous by continuous, and therefore this is continuous. So it is constant in finitely many subintervals, and it's continuous throughout. Therefore it's constant throughout. So this Y is answered. Basically piecewise. Yeah.
I didn't understand like why it should be constant throughout. Isn't that true for only complex functions?
Say it again.
T belongs to a T is a complex number here, right?
T belongs to the interval AB.
So how will that function be constant throughout?
Because you have a function defined here whose derivative is 0, let's say on a subinterval, then on that subinterval it's a constant.
Yes, sir.
Then it is 0.
Yeah.
Okay. Now there are suppose this AB is divided into two parts, finitely many. Let's do two. Okay. So AC and CB. On AC it's a constant.
Okay, I got it.
On BC on CB it's a constant, and it's continuous throughout. Therefore that constant value has to be the same.
Yeah. Got it.
What you can check is why piecewise continuously differentiable implies continuity. There's a small check required which you check. You must have checked long back, but just go back and check again. Okay, so continuity is there, therefore the constant is the same constant, therefore it's constant throughout. Okay, now we are done. Therefore, phi of B equal to phi of A. Why? Because this function is constant, therefore phi B by gamma B minus Z equal to phi A by gamma A minus Z. But gamma A equal to gamma B. Why? Because gamma is closed. starting point and ending point are the same. So phi b by gamma b minus z equal to phi a by gamma a minus z, but gamma a equal to gamma b, therefore phi b equal to phi a. And what is phi a? Look at the definition of phi. So what is phi a? Phi a is exponential of integral a to a of something, but if you integrate a to a, that is 0, and exponential of 0 is 1. So phi of a is of course 1. And therefore phi b is 1, which is what we wanted to show. Okay, so a small trick. This shows that it's an integer. Now here is a detour, slight aside. The question is, have you heard of this function called the Cantor function? Of course you have heard about the Cantor set. Have you heard about this function? How many of you have heard of Cantor function? Just quickly tell me. Unmute and tell me very quickly. We don't have so much time. Hariman, have you heard of Cantor function?
I just looked it up, and yes, I have. As in, I don't think I had known that name, but yes, I had seen that in the Stack Exchange post at one point.
Because Chirag, have you seen this before? You might not have seen, I guess.
No, sir, I'm seeing it now.
Yeah. Omkar, of course, must have seen, so I will not even ask. Mamta, have you seen this name before, Cantor function?
No, sir, I haven't seen it.
Okay. So I asked because sometimes in a measure theory course you might see this. Anyway, let's come back. This is not our topic. We will come back to it in the break. And of course, in the break, you can ask me, why am I talking about Cantor function suddenly? Okay. Or as you check the Wikipedia, you will know what is the relevance here. I mean, slight relevance, but let's come back to it in the break. So what is remaining now? We have shown that it's integer valued. I guess what is remaining is we have to show that it is constant in components. Right? Depending on gamma, you may have many components for omega, and we want to show that in a given component, the integer value that it's taking, that's a constant value. If it takes 5 at one point, it's the same 5 throughout that component. Now that's easy. We have done the hard part. This function, the index function gamma defined at z by that integral, this is a continuous function. Why is that? Why is this continuous? We have already seen this. Can someone quickly tell me why is it continuous? Okay, suppose it is continuous, then are we done? Because a component is a connected component, so continuous image of a connected set will be connected. So if this is continuous, image of a connected set will be connected, and the range is integers, right? So if it takes one integer value, for the range to be connected, it has to be the same integer value throughout that component. So it's constant on components follows because the image of a connected set is connected because this function is continuous. And this is continuous, we know already from last class. Why? Because we know that it is holomorphic. And holomorphic functions are differentiable functions, therefore of course it's continuous. And why do we know it's holomorphic? Because what is this index function? It is integral d zeta by zeta minus z. And we have shown that such integrals are representable by power series. These are representable by power series and therefore they are holomorphic. This we showed last time. And therefore the continuity follows. Therefore image of connected is connected and therefore in components it's constant. So that's also done. And this is done. Now the last bit is that the index is 0 if z is in the unbounded component. You can visualize the picture, no? There is a closed path, however you know funny the curve is, the path is, finally it's closed. It comes back to the starting point. So it's inside some big disk, and the outside part, right, that will be the unbounded component. So there's precisely one unbounded component, and there you have to show that this integer is actually 0. And this is also easy because if you look at the definition of the index, if you take right d zeta by zeta, so in terms of integral a to b, it will be gamma prime s ds by gamma s minus z. Now gamma star is compact, so gamma will take some maximum and minimum. Whatever it is, this d zeta by zeta part, there is a range beyond which it cannot go. So if you take z bigger and bigger, in the sense mod z bigger and bigger, this can be made smaller and smaller, right? In zeta, there is not so much range because of compactness of gamma star. Zeta is, there's 1 by zeta. It will have maximum and minimum. So by making mod z bigger and bigger, this can be made smaller and smaller. So in particular, if mod z is sufficiently large, this has modulus strictly less than 1. And the only integer strictly less whose modulus is strictly less than 1 is 0. So that's a proof. Note that the index function, its absolute value is strictly less than 1 if mod z is sufficiently large, and if an integer has modulus strictly less than 1, then it has to be 0. So that proves that in the unbounded component it is 0. This also you can think about why the name winding number. Why is the index called a winding number? So this also maybe we can discuss in the break. So let's take a quick break now. But before that, just one more statement. Just a beautiful observation. Suppose you take a positively oriented circle. So what is a positively oriented circle? It is parameterized by 0 to 2 pi a plus r e power I t, where t is ranging from 0 to 2 pi. That's positively oriented. Counterclockwise is positively oriented. So this will be a circle centered at A, going counterclockwise exactly once, right? Then observe that the index of z with respect to gamma is 1 if z is inside the circle and 0 if z is outside the circle. Here is a quick proof. If it is 0, if it is outside the circle, it's already done, because then it's in the unbounded component, and in the unbounded component it is 0. What if there is a point inside the circle? Then how do you show that the index is 1? What you know is the index of A with respect to gamma is 1, right? Index of A, suppose z equal to A, then you have to do 1 by 2 pi I integral dz by integral d zeta by zeta minus A. And there you can apply this parameterization, and it's a quick calculation that 2 pi I is the answer. So 2 pi I and 2 pi I goes, so the index is 1. So you know that this index, if you compute, it's an easy computation if it is at A. If it is at A. Now the only thing that you need to notice is that we have already shown that in components it's constant. So if z is from the same component as A, that means z is inside the circle, then the index is the same. Index values are the same, so index is 1. For z in the component of A, index of z is same as index of A, and it is 0 in the unbounded component. Clear? If you have any questions, we can ask, discuss in the break, and let's take a quick break and come back. And after the break, what will we do? After the break, we will prove local Cauchy theorem, that is Cauchy's theorem in a convex set, and then we will, as corollaries, we will prove Cauchy integral formula in a convex set, and also, what was the other one? Moreira's theorem. You know Moreira's theorem, right? It's a converse to Cauchy's theorem. If sufficiently many integrals are 0, then the function is holomorphic. So this also we will see. So let's stop recording and take the break.